Today I'm going to present our work titled Cosmos on Steroids, a cheap detector for cheap fakes. My name is Tankut Akgül. I'm an assistant professor at Istanbul Technical University. This work was done in collaboration with Tuğçe Civelek, Deniz Uğur, and Professor Ali Beğen from Özyeğin University. What do we mean by cheap when we are talking about cheap fakes? Cheap fake is altered multimedia content to deceive the audience without using advanced AI techniques, which would normally require more hardware resources and thus would make them expensive. Cheap fakes can be generated simply by speeding or slowing down content, or cutting, restaging, or recontextualizing footage. Here we can see an example of such alteration. There's a picture and two captions related to this picture. The caption at the top says parents who continue to put their children in booster cushions can continue to do so without breaking any laws in the UK. This is the genuine caption for this picture. The caption at the bottom, on the other hand, says backless boosters will be banned in the US starting in December 2016. This bottom caption happens to be the fake caption generated simply by altering the context. One thing to note here is though, by just looking at these two captions and the image alone, even us human beings cannot determine which caption actually provides correct information. We can only determine that the captions are out of context with respect to each other, or maybe with respect to the image itself. So the aim of Cosmos and this work also, given an image and two captions, is to determine whether one of the captions is out of context or not. It is not to determine whether the captions provide correct information or not. So how is this done in Cosmos? Suppose that I have an image and two captions and I want to know whether these captions are out of context or not. The first thing Cosmos does is to pre-process the captions to replace proper nouns with hypernyms, which are generic words like person, location, etc. So if I have a caption that says, for instance, President Biden gave a speech in White House, President Biden here is replaced by the word person, and White House is replaced by the word location. This step simplifies the interpretation of caption meanings in the next stages. Then the next reasonable thing to do might be to check semantic similarity of these preprocessed captions. If the captions are not similar in meaning, one of the captions may actually be out of context. However, this is not necessarily true. The captions are not similar maybe because they refer to different objects in the image. Therefore, it looks like one first needs to determine which objects in the image these captions are referring to before checking the caption's semantic similarity. This is exactly what the second stage of Cosmos is doing. It trains a model. I can give an image and a caption to this model, and the model tells me the alignment scores of the objects in the image with the caption text. Cosmos considers at most 11 objects, one of them being the entire image itself. Then in the last stage, which is the testing phase, Cosmos can finally look at the semantic similarity of the captions, and it uses an SBERT WK model for this purpose. Then it also checks the amount of overlap between the objects that these captions refer to, and it uses an intersection over the union score for this purpose. If the captions are semantically not similar and they refer to the same object in the image, then Cosmos classifies the sample as out of context. In all other cases, the captions are classified to be not out of context. This is the outline of the Cosmos algorithm. Let me explain this final step with an example, hopefully for a better understanding. In this example, there's a photo which shows a bridge-like structure, and there are two captions which both talk about the bridge in the image, and they both convey some message. So the Cosmos algorithm first runs the image and the captions through the trained model to find the maximally aligning object with each caption. In this case, the maximally aligning object for both captions is the bridge itself. Then the semantic similarity of the captions is checked. Since these captions convey a different message, they are actually semantically different. And since they refer to the same object in this image, the image caption pair is classified to be out of context by Cosmos. On the other hand, imagine these captions talked about different objects in the image. Let's suppose one about the bridge and the other one about the Eiffel Tower at the back. Then obviously the captions would have low semantic similarities still. But in this case, since the objects would be distinct, it would be okay for the captions to be semantically not similar. In this case, the model would predict the captions to be not out of context. There are a few problems with this approach though. First of all, captions that have opposing or conflicting meanings or that explicitly include words such as fake, hoax, etc., which strongly indicate that the caption may be out of context, may still have high semantic similarity scores. We have observed that this is mostly the case when the captions contain common words but convey conflicting messages. We think that this somehow tricks the expert WK model that Cosmos uses for similarity checking. Secondly, in the original Cosmos work, the caption alignment is carried out against the caption and a single object in the image, which happens to be the most aligning object with that caption. However, a caption may refer to multiple objects in an image, so even though captions may appear to be unrelated, this may be because they simultaneously refer to multiple distinct objects in the image. Finally, the IOU threshold in the original Cosmos work was taken as 0.5, that is midway between no overlap and full overlap. What we have observed is that when the captions are actually in context, even though they are not semantically similar, they typically refer to distinct objects which only slightly overlap or do not overlap at all. So in this case, their IOU score is actually typically very low. Therefore, the IOU threshold can be biased toward these symbols, which will reduce the amount of false negatives, that is, captions that are actually out of context, but classified as not out of context. And I'll explain this later in the presentation. So given these problems we have observed, we have 4 different methods shown in this slide that try to address these problems. These are differential sensing, fake or fact, Object-Caption Matching improvement, and the IOU threshold adjustment methods. So let's look at each of these methods in more detail. Our first method is what we call differential sensing. In this method, we generate 2 reference captions, which we call the positive probe and the negative probe, using one of the given captions by appending was true and was not true to it. As an example, suppose one of the given captions is the following. The picture shows there was an earthquake in location. The positive probe becomes the picture shows there was an earthquake in location was true. And the negative probe becomes the picture shows there was an earthquake in location was not true. Then we calculate the cosine similarity of the original captions against the positive probe and the negative probe. Cosine similarity is taken between the embedding vectors given by the S-BERT model. We expect that if the original captions have parallel meanings, their similarity score switching from the negative probe to the positive probe will change in the same direction. That is, both captions will align better with either the positive probe or the negative probe. However, if the captions have opposite meanings, then one of the captions will align better with the positive probe, but the other one will align better with the negative probe. So switching from the positive probe to the negative probe, the similarity scores of the captions will change in different directions in this case. So in the diagram on this slide, caption 1 and caption 2 have non-conflicting meanings because switching from the negative probe to the positive probe, the cosine similarity score increases for both captions. On the other hand, caption 3 and caption 4 have conflicting meanings because switching from the negative probe to the positive probe, while the similarity score against caption 3 increases, the score against caption 4 decreases. This is an example image caption pair where Cosmos fails to label correctly. We can see here that the 2 captions actually present conflicting information, but their S-BERT similarity scores are high, maybe because the captions share common or similar words such as engine, aircraft, and repair. Consequently, Cosmos labels these captions as not out of context. However, using differential sensing, Our method can detect that these two captions actually contain conflicting information and thus can label this image caption pair as out of context correctly. The second method is the fake or fact method. In this one, the aim is to actually detect whether one of the captions contains offending words, signaling that the caption actually has misleading information. These are words like hoax, fake, fabrication, disinformation, etc. This method works more like a spam filter actually, looking for a special word or a list of words in an email to classify the email as spam. For this purpose, we generate a test caption simply by comma separating a list of words that may indicate the caption is out of context. Then each caption is compared against this test caption by taking the cosine similarity among the embedding vectors of the caption and this test caption, which is obtained by the Expert model. If one of the captions indeed contains such words, its similarity score happens to be much higher than the similarity score of the other caption, which doesn't include these words. So in this case, we can predict the caption or the sample as out of context. And here's an example for fake or fact method. Cosmos labels this image caption pair incorrectly as not out of context. On the other hand, our method labels it as out of context because the cosine similarity score happens to be significantly higher for the second caption compared to the first caption. And this is due to the fact that there's a phrase not genuine present in the second caption. In the improved object-caption matching method, we find multiple objects, if more than one exists of course, that maximally align with each caption. Then we combine the bounding boxes of these objects simply by taking a union over them. The resulting bounding box provides a better visual object grounding with each caption. Finally, we compute the IOU score between these combined bounding boxes instead of the bounding boxes of the single objects in the original Cosmos work. Here's an example of this method being applied. On the left-hand side, we see the image which contains a tank and a woman carrying a bag of crops. When the Cosmos trained model runs, both captions happen to align mostly with the woman as shown by the green and the red rectangles on the left image. The IOU score of these rectangles is 1 since they perfectly overlap. Moreover, because the captions have low semantic similarity, Cosmos labels this sample as out of context. However, when we look at the captions closely, we can see that the captions actually refer to the tank and to the town also. Especially in the second caption, both the woman and the town are mentioned simultaneously. For this reason, the woman and the entire image alignment scores with the second caption are actually very close. Therefore, our method merges the rectangles of the woman and the entire image, resulting in a bigger rectangle as shown in green in the picture on the right. Since the IOU score of this bigger green rectangle and the red rectangle surrounding the woman is not large anymore, our method correctly predicts this sample to be not out of context. The final improvement is the IOU threshold adjustment. As I mentioned before, when captions have low semantic similarity but are actually not out of context, they typically refer to distinct objects in the image. Therefore, the IOU scores are very low in this case. So if you look at the plot on the right here, the blue samples are the not out of context samples, and they are concentrated on the left-hand side of the plot. Therefore, we can decrease the IOU threshold. By doing this, the OOC samples, which are out of context samples, which are missed earlier, have their IOU scores higher than the new threshold now. So they are not missed anymore. On the other hand, since most of the not out of context samples are still concentrated below the new threshold, we do not add many more false positives either. And this slide shows an example of this method applied to an image caption pair. These captions are actually out of context, but since the IOU score of 0.33 is below the threshold of 0.5, which Cosmos uses, Cosmos unfortunately misclassifies these captions as not out of context. When the threshold is decreased though to 0.25, This no longer happens, and we can classify the sample as out of context correctly. And here are the results for Cosmos on steroids. In the table, the baseline model represents the original Cosmos model. We have achieved an 81.9% accuracy with the provided test set, which has 1000 images along with their caption pairs. Note that the 85% accuracy reported in the Cosmos paper is with a larger test set not shared by the challenge organizers. And the table shows the accuracy improvement when each method applied on its own above the baseline model. When all methods are combined, we achieve a 6.4% overall improvement. And if we look at some other classification performance numbers, we can see that our model achieves a total of 85.8% precision and 91.8% recall. Looking at the runtime performance, we achieve 76.71 milliseconds per sample inference time. Finally, regarding the model size, our only addition on top of the baseline model is the SBIRD model that we use. And we use SBIRD instead of SBIRD WK because this resulted in better classification performance in our tests. On the other hand, since SBIRD has smaller model size, we could replace SBIRD WK used in the baseline with this as well, which would actually reduce the overall model size below the baseline. But we didn't want to do that because the SBIRD WK scores were already provided in the test set. In summary, we have made some changes to Cosmos to improve the out-of-context caption detection accuracy. However, there is still room for improvement if you consider cheapfake content outside the limited context that we address. For instance, in a more general context, a picture like the one shown here may have two captions where both captions are related to the image. However, one of them gives fake information about the place of the fire because the captions refer to different cities. Since city names are replaced by their hypernyms, this discrepancy will not be visible to Cosmos in the first place, even with our improvements, by the way. However, even if there was no text preprocessing, it is not possible to detect a cheapfake like this without knowing that the place names are actually referring to different cities. So extra source of information may be needed to identify these cases. And this concludes my presentation. To download the code and test it, you can use the barcode on the slide. And if you have any questions, you may reach us using the given contact information. Thank you for your attention.